Now, upon page fault, what happened? Execution transfer is given to the operating system by interrupt mechanism. I hope you remember what is the interrupt mechanism is from your computer organization classes. Operating system keeps track of like copies and location of the pages of a process in the disk, and each individual physical page and its recent usage history, so that it can basically look at which page to replace. Okay, it runs an algorithm to page replacement algorithm as suitable. Now, upon page fault service request, we perform following steps. Deploy maybe an LRU to choose a physical address to be replaced. Just I gave an example as an LRU, but there are more advanced technique, basically replacement algorithm than LRU. First, the replace the physical page stored back onto the disk if it is dirty. You know what the dirty means. Let's say the page has been written, so we need to first replace, like put it back to the disk, and then the new page from the disk is to return into the physical page. Then processor page table is updated with the new physical location, and control is returned back to the actual program. Now, you might ask here in this point, your translation table, where it is. Where is that translation table resides? Where that page table register points to. To understand this slide about TLB or translation look-aside buffer, we need to first understand where this virtual page address to the physical page address map resides. Okay, so this map, which translate virtual page address to the physical page address, resides in a primary memory, the RAM, in the part which is assigned as a reserved area. If you recall our computer organization study, in any processor we studied MIPS, and it's true for the x86 and other ranges of processor, that a part of the main memory address space is treated as a reserved space which should not be touched by any user program. It is usually the lowermost section of the memory address space. So at that point, I mentioned that in the previous class, like CS147 computer organization study, that we do not need to know what the usage of that area, and we'll see it in 147. And now it is the time at the end of the CS147 computer architecture study. Now we understand what this reserved space is for. This is the place where system stores information to maintain and run the whole computing system as a whole. This is in conjunction with the operating system as well. So this computing system stores this map, virtual memory to the physical memory, that map in the RAM address, that reserved space. Now place this concept in context of the cache access. Remember, the cache memory is all about faster memory access at the L1 or L2 level, which resides inside the processor chip as a whole, right? Now think, we are using cache system, and also we are using virtual memory system in the same computing system. That means processor is issuing a virtual memory address to be accessed, and which first need to get translated to the physical address, and then corresponding cache needs to be accessed if it is present in the cache, if that data is present in the cache. Now look at this virtual memory translation. To do that, if my virtual memory map resides in the RAM, we already have lost our context to increase performance using a cache, right? Because even before accessing the cache, since we are using virtual address, we first need to access the RAM, which is slow already, right, compared to the L1, L2 caches. So our purpose is gone there, right? So for that reason, a part of this map is stored in cache memory. Okay, and that part is called a fast TLB, or translation look aside buffer, or translation look ahead buffer. One of the term is there. We usually call it a TLB. The faster address translation, because a part of the map is present on the cache. Now, why it should work? It should work with the same reason as the cache work. Like, cache works based on your locality property, right? It's based on your temporal locality and your this locality, your spatial locality. That means if an address is accessed once, it probably likely to be accessed many more time in near future, and its surrounding would be accessed many more time in near future. That means, like, if even if the address is virtual, that fact is true. And if that fact is true, then if we only need at a time only a part of the virtual memory map into the cache. Okay, so we don't need to load the entire virtual memory map into the cache, but only part upon which it will probably be hit more often. Translation will happen more often through that part of the map residing in the cache, because of the software's property of locality. So now what happens, your virtual page number is generated, and then it is being referred with the map on the cache with the same mechanism as in the tag and matching of the tag. So your virtual page number in this mechanism is broken up into tag and the index. So that corresponding index line is accessed, tag is matched, and if the tag is matched, corresponding physical page mapping, we know it exists there, and it contains and accesses that physical memory.